Good afternoon, everyone, and welcome to today's webinar. My name is Jacob Hayden, and I'm the program coordinator for SaferSim at the University of Iowa. SaferSim is a Tier 1 university transportation center with the research priority of promoting safety, and our webinar series features the research projects from within our center. So thank you for joining us today. There will be time at the end of the presentation for questions and discussion, and attendees can use their microphone or the chat box to participate, since we're all probably familiar with Zoom now. But feel free to use your chat box at any point throughout the presentation as well, and we will address those questions or comments when we can. Today's webinar features a research project from the University of Iowa's Hank Lab, and it examines conflicts between bicycles and vehicles. So I'm pleased to welcome our presenter, Lakshmi Subramanian.
Thank you. Um, Welcome everyone. So today's presentation is about the project which we carried out. The title of the paper is Using Simulation to Access Right Hook Conflicts Between Bicycles and Cars at Protected and Unprotected Intersection. So as we know, the separated bike lanes are popular. The advantages of the separated bike lanes is it helps to have increased safety because there is a separate place for the bikes to ride in the road, and also it helps to regulate high traffic volumes. So the problem with the current bike lanes is uh, the right hook crashes. As we can see in this figure, um, a car is trying to make a right turn, and we see a bike is also trying to cross in the same path as the vehicle. So there is high risk for right hook crashes. So this present a significant threat to the bicyclist safety. So this is a current problem with the separate bicycle lanes which we have. An alternate or a new infrastructure for the bicycle lane is protected intersections. So this is an image of the protected intersection. It's just an example geometry. So as we can see, it has many elements in increased safety, increased width for the bicycle to ride. And then we have some of the elements in the protected intersection, like a corner refugee island, a forward bicycle queuing area. This is a motorist yield zone, and separate by pedestrian and bicycle crossings. So this is an example geometry for the protected intersection. Some of the current studies which analyzed this protected intersection says that it improves visibility for the drivers. So the driver has more time to react because of the larger turning radius. And also some of the field studies which were carried out shows it has led to reduced turning speeds, and also reduce the frequency and severity of collisions between drivers and bicyclists. So the question we have is, how do bicyclists will respond to such protected intersections? Because the studies which so far have analyzed only drivers' point of view and drivers' behavior towards such infrastructure. So in this project, we are analyzing bicyclist response, particularly to the right hook crashes or the right hook turns. So we have the bicycling simulated in the Hank Virtual Environments Laboratory. So it is a three-sided cave, and there is a rear projectors which project image onto the cave, and there is a front projector that projects onto the floor, as we see in the image here. So we have the head tracking done by the cameras mounted on top of the cave, and there is a sensor which is mounted in the bike, so that the visual angles for the bicycle are according to the image displayed. So when the bicycle moves, the visual angles get adjusted, so it looks like as if riding in the real world in a bicycle. except we are doing it in a virtual simulator. So we are comparing the protected intersection with the unprotected intersection. So this is a screenshot of our scenario. As you can see, the protected intersection has a larger turning radius. We have the island here, corner island, which is called the refugee island, and we have some extra space for the bicycle path. But whereas in the separate bicycle lane, which is a typical lane, yeah, it's just a typical bicycle lane which we see in our everyday life. So what we are going to analyze is how bicyclists are going to respond when cars make a right turn and just come across towards their path. So we have done 4 experiments, all are between subjects. So we have protected treatment, protected control, unprotected treatment, and unprotected control. In the protected treatment, we have cars. Half of the cars will go straight and half of the cars will make a right turn. They are randomized. And in the protected control, all the cars will go straight. Similarly, same for unprotected and treatment. Half of the cars will turn right and half of the cars will go straight. But whereas in control, it's just the straight cars. The manipulation we have is among the turning vehicles, they are said to arrive at the conflict point, so which I'll be explaining now, at 1 or 1.5 seconds before the bicyclist time of arrival. So I have a picture here. So it's just a layout of protected and unprotected intersection. So if we see here in the left-hand side, which is a layout of the protected intersection, so this is the measurements for one particular intersection. So all the intersections in the experiment are identical. So we have a road, which is like about 104 meter length. So a point about middle of this intersection is called the trigger point. So when the bicycle, as he's riding towards the trigger point, when he reaches the trigger point, the car generation is initiated. So this particular place where the car begins to make the right turn is called intersection entry point. And this red color star, which is present here, is called conflict point. So the car, once the bicycle reaches the trigger point, the car generates such that it arrives either 1 second or 1.5 second before the expected time of arrival of bicyclists at the conflict point. Similarly, straight cars are also generated in such a way they arrive 1 or 1.5 seconds before the conflict point, except they don't turn, they just go straight. Similarly, in the unprotected intersection also, we have a layout here. So this is the trigger point, which is the blue color star. So once the bicycle reaches trigger point, the car generation is initiated. And this is an intersection entry point, because from this point onwards, it's the turning cars will begin to make turn. So this is the conflict point, the point at which the bicycle and the car meets. So overall, in our experiment design, we have half of the vehicles which turn and half of the vehicles which do not turn for the treatment conditions. Among the turning vehicles, and both the straight and the turning vehicles are randomized to arrive at conflict point 1 or 1.5 seconds before the bicyclist predicted time of arrival. So this is a screenshot of how it looks when the car is present at the intersection entry point. So this is the intersection entry point here. Similarly, this is a car at conflict point. So these are the screenshots taken from the Unity. So when the car is at conflict point, this is how it behaves. Similarly, for protected intersection, you can see the top-down view and the side view for car at intersection entry. And car at, this is the next slide showing how the car is present at the conflict point. It's expected to arrive at the conflict point based on our timings. So the procedure is the participants are expected to ride straight. So there are 24 intersections. They just want to make sure they're not hit by cars. So for the analysis, for the turning vehicles, we are analyzing these two, margin of safety and bicycle speed. And for the straight vehicles, we are analyzing separation at intersection entry and bicycle speed at intersection entry. Then for all the vehicles, we are analyzing speed trajectory and maximum deceleration. So the task is for the bicyclist is to ride straight without getting hit by car. There are 24 intersections. Each intersection is a trial, so there are 24 trials. So let's see the conflict point analysis. So for the conflict point analysis, first thing is the margin of safety at conflict point. So when the car reaches conflict point, what is the position of bike at that time? Because the car is expected to arrive either 1 or 1.5 seconds before the expected time of arrival of bike. So definitely the car is at front of the bike. So at that time, when the car reached the conflict point, we just take the position of the bike and we are finding the difference between the bike and the car. So this is the margin of safety. So we used mixed effect linear regression. So we found that riding protected intersections were predictive of 2.66 meter increase in distance between the rider and car at the conflict point. So as we can see in the diagram here in the left-hand side, so there is an increased distance when the bicyclist is riding in the protected intersection than in the unprotected intersection. Similarly, for the late arriving cars, so as I mentioned, there are two timings, 1 and 1.5. So the 1.5 second is termed as early cars and the 1 second is termed as late cars. So the late arriving cars predicted a 2.40 meter decrease in distance between the rider and car. Next is the analysis for the rider speed at the conflict point. So the late arriving cars were associated with 0.20 meter per second reduction in bike speed compared to early arriving cars. So we are comparing the turning cars present in both the treatment condition for protected and unprotected. In the next analysis, this is a separation at intersection entry for straight going cars. So here we are splitting the analysis. So first we are analyzing only the protected intersection for both control and treatment, only the straight going cars. So let's see. So for the protected intersection, when we analyze only the straight going cars for the control and treatment, we see a main effect of condition, which is being in the protected treatment condition predicted at 1.62 meter increase in distance between the rider and car at intersection entry point compared to those in the protected intersection control condition. So when the car is at intersection entry point, the bike is at increased distance for the treatment group, not for the control group. Similarly, for the unprotected intersection, the graph on the right hand side, so we are analyzing the straight going cars for control and treatment. So we found main effect among the early arriving cars only. So based on car arrival time. So the early arriving cars were associated with 2.75 meter increase in separation between the rider and car compared to late arriving cars. So so in general, the bicyclist in treatment condition had more room between themselves and the car for the straight going cars. So this is analyzing the bicyclist speed for the straight going cars at the intersection entry point. So we didn't see any significant difference with the speed for both the protected and unprotected conditions. The speed was almost same for the bicyclist when the car reached the intersection entry point. So next we'll go for the speed trajectory analysis. So as we can see here, we analyzed the speed of the bicyclist starting from the trigger point up to 60 meters from the trigger point. So as I showed in a layout diagram before, so starting from the trigger point, the 50 meters from the trigger point is a conflict point. So that's where we see the greatest dip in the speed. So we analyze the trajectory across the layout from the trigger point till 60 meters from the trigger point. So as we can see, the protected conditions overall have the greatest dip in the speed. The lowest speed was reached in the 10 meters before the intersection. participants in the protected intersection showed a greater dip in speed than those in the other conditions, which is seen in the graph here. We also analyzed the deceleration. So this was computed as a difference between speed in the bin with the slowest average speed and the speed at trigger point. So first, let's see only the treatment conditions. So when we see only the treatment condition, that is protected intersection treatment and unprotected intersection treatment, the protected treatment has a 0.32 meter per second square maximum deceleration compared to unprotected treatment. This is consistent with the conflict point analysis. Next, when we analyze only the control conditions for the protected and unprotected, we see the protected control has 0.13 meter per second square maximum deceleration as compared to unprotected control. So as we see, among the control conditions, there was only straight cars. So the participant didn't experience any turning cars. So this is the effect of pure geometry of the protected intersection. So the geometry of protected intersection makes the rider to have a high deceleration compared to the unprotected intersection. So when we analyze just the protected intersection treatment and unprotected treatment for the straight and turning cars, because in the treatment condition only the participant experienced both the straight car and the turning car. So when we just analyze this, we found the significant main effect of condition. The protected treatment condition was associated with 0.47 meter second square maximum deceleration. 0.13 meter second square maximum deceleration compared to straight going cars. So similarly, riders in the unprotected intersection did not demonstrate a differential response to turning cars. So in this second table, we see when the participant experienced both straight and turning, he definitely had a greater reduction in speed overall compared to unprotected participant. So what are the takeaways here? We see in generally there was a greater distance between the rider and cars when making the right-hand turn. Particularly, the people in the protected intersection showed greater dip in the speed because those are the people who experienced both the straight car and the turning cars. But whereas when we analyzed only the control conditions, still the protected control showed a greater deceleration and reduction in speed. The average speed of participants was lower for turning vehicles that arrived late to the conflict point as compared to those that arrived early. Even for the straight going cars, there was a greater distance for riders in the treatment than in the control. So this demonstrates overall the protected intersection, the geometry and the influence of the turning cars had a positive influence on the riders to ride safely. So the riders adjusted in the moment to vehicle approach. So based on all our analysis, overall we see what is the reason for riders to have more distance between themselves and the car in the protected than in the unprotected is first is the geometry. So the geometry of the protected intersection enables riders to have better view of the car. And also it enables them to reduce the speed as they approach the intersection. And second, because of the influence of the right turning vehicles. So overall, we see that protected intersection can increase the bicycle safety. We thank our sponsors for supporting this project. Thank you everyone for listening to my presentation.
Thank you, Lakshmi. That is interesting work. This will be our final presentation for 2020, but we're still scheduling more for next year, so stay posted for future announcements. So with that, thank you all for joining. Enjoy the rest of your year, and we'll see you again soon. Thank you, Lakshmi.
Thank you.
Thank you very much for the presentation.